Okay, let's go ahead and jump in. Um, so let's stop my video. Okay, so we're going to jump into basically the third part of the course, kind of we take what we've learned about with respect to normal distributions and we apply them to making predictions. Okay, we want to make predictions now using the normal distribution and the probabilities that we covered in the last sections. Okay. Okay, 8.1, 8.2. Okay, confidence intervals to estimated population mean. Okay, mu. Okay, objective number 1, perform and create and interpret a 1 sample t interval for a mean. Okay, calculate the sample size needed to achieve desired margin of error. Okay, so those are our 2 objectives. Okay, recall sampling distribution of all possible sample means. Okay, remember we talked about all the sample means. There's means plural. Okay, so that's a plural means on there. Okay, so we would take an average. We would look at our population and we take a sample of that population, and then we would average that amount. And then we would take another sample and average that amount. And then we take another sample and we would average that amount. And all the samples are going to be the same sample size, and they're all going to come out of the same population. And we said that if we took enough of these samples, that all roads would lead to a normal curve. Okay, and so you would get X bar here, X bar here, X bar here. I don't like my X bars. Okay. This would be the middle. Okay, and this is called the central limit theorem, saying that as we get more and more and more and more, they will become a normal distribution. Okay, so X bar, X bar, X bar, X bar, X bar, X bar, X bar. That's a sample mean, that's a sample mean, that's a sample mean, that's a sample mean, that's a sample mean. Most of the sample means are going to have the same characteristic as the true mean, right? As the population mean. Remember, X bar is the statistic, that's the sample mean, and mu is the parameter, that's the population mean. Okay, so if we take a bunch of X bars, okay, and we do this over and over and over and over again, then the more that we get, the closer to this bell-shaped curve that we get. Okay, so we get X bar here, X bar here, X bar over there, okay, maybe one over here and one over there. Okay, the distribution of sample means is, what is it, do you think? It is approximately normal, right? Okay, it's approximately normal under a couple of conditions. Okay, distribution of sample means. The original population distribution is normal. That means that the parent distribution was normal. Okay, this is the parent population was normal. I'll just call it Z, okay, for a normal curve. Try to draw that a little bit better. Okay, Z, right? Z is our standard normal curve. Okay, population distribution was normal that it came out of. Okay, so of all these random samples, the parent, okay, the parent was a Z curve or a normal curve, then the child in which the samples are taken out of will also be normal. Or the sample size n is large enough. And usually that's n is greater than or equal to 30. Okay, if I take at least 30 samples, then it's going to have a normal distribution, or approximately normal, if I take more than 30 samples. I need at least 30 samples. So even if the parent was a skewed distribution, even if the parent was skewed, I know that we have a lot of skewed parents these days. That's a joke. Okay. So if the parent was skewed, but we take at least 30 samples, okay, at least 30, and what are the samples? That's not the number of individual data points, though. These are the means. N, okay, n of x bar, I should say, maybe. N of x bar, right? That's the number of averages that I took. If the number of averages that I took is at least 30, even if the parent is skewed, what does the child look like? Well, the child looks like this guy here. Okay, he's still a bell-shaped curve. This is called the central limit theorem, or CLT for short. Okay, it says, look, all roads, if I'm dealing with sample means plural, okay, sample means, not just one sample, a bunch of samples out of the same population, then this will lead to a normal distribution. Oh, okay. Okay, this normal distribution has mean of population mu, which we've seen before, and standard deviation of population sigma over the square root of n. Okay, that's the standard deviation for the sample means. Okay, example 1. Suppose that the students at a large college are currently taking a mean of 11.2 units. Okay, so this is a large college, right? So is this the sample mean or the population mean? Sample mean or population mean? Well, it's a population because it's all the students at a large college. Okay, so maybe let's say that it's UCLA. Say that there's 25,000 students at UCLA. Right? 25,000 students. I mean, that's a small city. So there's a small city amount of students there, a large college, and they say that the mean is 11.2 units. So I'm going to say, oh, that's mu. Okay, that's mu. Okay, that's the population parameter. With a standard deviation of 4.4 units. Okay, what's that guy? 4.4. Well, that's sigma. That's the population standard deviation. I just like saying that. Okay, population standard deviation. It just rolls right off the tongue like Dalmatianization. Okay, anyway. That's from 101 Dalmatians, by the way, if you didn't get that reference. Okay, anyway, whatever. Okay, it's a population standard deviation on our Dalmatian plantation. What a sensation. I need to stop. Okay, 52 students at the school are randomly selected. Okay, randomly selected and asked how many units they're taking. Okay, 52 students at the school are randomly selected and asking how many units they're taking. What is the probability that the sample of 52 students has a mean greater than 12 units. Okay, so how many samples is this? How many samples am I taking? Not the number of students, but how many samples am I taking? I'm only taking one sample. Okay, and since I'm only taking one sample, okay, and we're going to assume a couple of things. We're going to assume, number one, that the sample was independent of each other. The samples are independent of each other. Okay, that the samples are random. Okay, and that the samples came from a large population. Okay, then this fits the criteria for me using the normal distribution. Okay. Okay. So since 52 is greater than or equal to 30, okay, okay. And so what I'm going to do is I'm going to take this sample, one sample, and then I'm going to do it over and over and over again. And I'm going to get multiple samples of 52 students. Multiple times. I'm going to take a sample multiple times. One sample 52, multiple times. One sample 52 times. And since 52 is greater than or equal to 30, then the central limit theorem applies. And we can use a normal distribution with mu equaling the population. This should really be mu x bar. Mu x bar equaling the population distribution, which is, okay, they're saying that the mean is 11.2, right? Okay, that goes back to the population mean. But the standard deviation changes because instead of sample sizes of 1, I took sample sizes of 52. Okay, instead of sample sizes of 1, I'm taking sample sizes of 52. Okay, and so this becomes sigma over the square root of n, which is 4.4 over the square root of 52, which is approximately, let's see, what is that approximately? Second quit. Okay, 4.4 divided by the square root of 52. And I'm getting about 0.610, is that right? 0.610, yeah, 0.610 or just 0.61. Okay. Okay, so now I want to find what's the probability that they will have, that the students, 52 students, has a mean greater than 12. Okay, mean greater than 12. So I kind of ran out of room here, so I'm just going to go up here. Okay, and I'm going to say, okay, well, we know that because it has a central limit theorem. The graph sucks. Okay, then all roads lead to a normal distribution. we know that the mean, okay, the mean is 11.2, and we want to know, okay, we want the probability that the mean for any 52 students, the mean for any 52 students that I were to grab is 12 or higher, okay, is greater than 12. Okay, so we would do a normal CDF, okay, on this, and it would go from 12 to infinity, okay, from 12 to infinity with a mean of 11.2 and now a standard deviation of not 4.4. That would be only if I was picking groups of 1. Okay. Okay, now I'm picking groups of 52. So this becomes 0.61. Okay. If I plug that into my calculator, second VARS, normal CDF, the lower is 12. The upper is infinity, so I'm going to do 1e to the 99. Okay, the mean is 11.2, and the standard deviation is 6.1. Nope, sorry, 0.61. 0.61. Okay, and that gives me about 0.04. So this is 0.0949, or about 9.5% of the time. About 9.5% of the time. Okay. Okay, considering the same parameters that we're dealing with as before, we want to find a range of usual values for X bar, usual values for X bar. Well, those are going to be values that are within 2 standard deviations of each other, right? Plus or minus 2 standard deviations of each other. Those are going to be my usual suspects. Okay, so U of X bar is equal to, what do we say, 11.2? Sigma of X bar is equal to 0.61. So what do I want? I want 11.2 in the middle, and then I want to go out 2 standard deviations above and down 2 standard deviations below. So if I add 0.661 twice, okay, so 11.2 plus 2 times 0.61, if I add that twice, I get 12.42. If I take 11.2 and I subtract 0.61 twice, I get 9.98. So what do I know? I know that these values within 2 standard deviations, okay, or 95% of the values in this within 2 standard deviations in this scenario are between 9.98 and 12.42. So 95% of values, okay, are in this range. Okay, they are in this range. Okay, and what we're going to see is that this range of values is called a confidence interval. We're going to talk about what does that mean to be a confidence interval. This range is called a confidence interval. Okay, we are 95% certain that the true mean is, okay, is within that range. Okay, the true population. Okay, in this case it is because that's what we used. We used the true mean as the sample mean, but sometimes we're not given the true mean, and we have to kind of make an educated guess as to where it is. Okay. Okay, definition, point estimate. Point estimate is a single value estimate for a parameter. Remember, parameter is population. Okay, X and sample is for statistic. Estimate is for a parameter. X bar is the best point estimate for mu. Okay, so if we don't have mu, we use X bar. That's our best estimate. Okay, and the larger our sample size, the better that estimate gets. Okay. Interval estimate, the range of good estimates for a parameter is X bar plus or minus 2 standard deviations is a good interval for estimates for mu. This is if I don't have mu, if mu is unknown. How would I estimate what the true parameter is? How would I estimate what the true parameter is? That's a mu, not an M. Mu. Okay. If mu is unknown, that's what we're looking for. If mu is unknown, where would be a good place to look? Okay. Say that you lost your car keys, and your car keys, in this case, was the population mean. And you're like, do I want to look in the house? Do I want to look in the car? Do I want to look in the yard? Well, if the car keys, if I can look at some other values for the car keys, then I can say, oh, maybe I want to be close to where I was last. And that's going to be a good range of values to look for my car keys. And if I hadn't been in my car for like 3 or 4 days, that might not be a good place to look. Okay. So it's kind of the same thing here. We want to know where's a good place to look for our car keys, where's a good place to look for the mean. We don't know the mean, but we want a good place to look. Okay. You must specify 2 things in every confidence interval. You must get a range of values, or what we call an interval estimate. Okay, confidence intervals are interval estimates for estimating a parameter. And what are our parameters so far that we know about? We know mu and we know p, right? And we know sigma. Okay, those are our parameters that we've been working with. Okay. Today we're just going to deal with the mu and sigma and not worry about p until Thursday. Okay, it's a long time to wait to p. Sorry. Okay, that's inappropriate. I need to stop that. Okay, there's just a lot of p-values in statistics. Okay, number 2. Okay, we also need to know what's our confidence level. How confident am I that my car keys are within a certain boundary? How confident? Am I 90% confident? Am I 80% confident? Maybe being in the house is only 80% confident, but if I include the house and the yard, now I'm 90% confident. If I include the house and the yard and the bottom of the pool, then maybe I'm 97% confident. Right? So as the area increases, I'm more and more confident because there's less area where it could be out of that. Okay. Okay, confidence levels. Confidence level is the success rate of the procedure used to construct the interval. Okay. For example, if we use a 90% or 0.90 confidence level, then 90% of all possible samples of size n would produce an interval that contains a true parameter. So if I do a 90% confidence interval, say that the interval was from, I don't know, 1.5 to 6.5, then I am 90% confident that mu, the true parameter, is between those numbers. Okay, that means that I'm 90% confident that 7 is not going to be the true mean. Okay, this gives us a place to guess. Are we ever going to be 100% confident? No. Okay, could the keys be in Disneyland? Sure. Okay, I don't know. Maybe somebody stole my keys and took them to work and now they're, you know, on Mr. Toad's Wild Ride. I don't know. I'm not 100% certain that the keys are anywhere near my house, but there's a high probability that they are. So we're never going to be 100% certain. Okay, that's why the wider you go out, the higher the confidence level. But I could include the entire Earth in, you know, my analogy. It just, that would make it 99.999999999% certain that my keys are on planet Earth, right? But there is that always that 0.0001 in a billionth trillionth chance that it could have been thrown on a satellite. I don't know. Okay. Okay. It's the cars to the, it's the keys to the car that's the Tesla that's floating in space. There you go. Except I don't own a Tesla. We won't even go down that route. Okay. That means 10% of the time, the interval produced would fail to capture the true parameter. Okay. We say that failure rate, or 1 minus the confidence level, 1 minus the confidence level is equal to alpha. Okay. Alpha is just a Greek letter A. That's all it is. And if it's 10%, then alpha is 10 as 0.10. Okay, 1 minus the confidence level, CL. Okay. Okay, then that's 10%. Okay, so let's look at a visualization here real quick that I have up. Okay, hopefully you guys can see this visualization. Okay, so is that the right visualization? Maybe we won't do this one. I want to go back to sampling distribution. I want a sampling distribution for mean, not proportion. There we go. Sampling distribution for mean. Okay, sampling distribution for a mean. Okay, so we have a sample size of 10. I do not want sample size of 10. I want sample size of at least 30. Okay. Okay, so sample size should be 30. Okay. And then I can generate, okay, this is percent of internet access in countries. Okay, I don't know. Statistics of grad schools. Oh, there's a bunch of things that I could look at. They have all this data online that you can you can mess around with. Number of people in a band. That's kind of cool. Rock performers, people in a band. You got big bands and you got small bands, right? Okay, so let's do n equals 10. Well, let's do n equals 30. Okay, so that's 30 samples, okay, out of all the people who were ever in a band. Okay, this thing's going to be the original population. If you look over here, is very much right-tailed. Does that make sense? The population is very much right-tailed. Why? Why would it be right-tailed for the number of people in a band? Well, that's because generally you're going to have what? Like 1, 2, 3, like you have all of these single artists, right? Okay, all of these single musician, and then maybe you need like 4 or 5 people in a band. You got your drummer, right? And your guitarist and your bassist and your person that does your wind instruments and your keyboardist. Okay, and then this is like 12 people in a band. Man, that's big. That's like if the Jackson 5 met the Brady Bunch, they would form a 12-person band. That's a big band. Okay, but you can see that the population here, okay, is right skewed, right? Okay, it's skewed to the right. Okay, but if I take enough of these means, what should my population look like? If I take enough means, what should the distribution look like? Well, it should hopefully approximate. Okay, this is just one data point, right? So they ran a bunch of data and they said, oh, we got 3.8 as our average. Okay, let's get 10 samples. 10 samples, we get 3, about 3 people as our average. If I generate 100 samples, I get 2.807 as my average. And if I generate 1,000 samples, look at that. We took something that was right skewed, okay, right skewed, and we turned it in to a approximate standard deviation, okay, approximate normal distribution, not standard deviation, okay, where the mean is about 2.877. The mean here matches closely to the mean of the original data, but the shape is completely different. The shape of the data is completely different. That's because this is the distribution of the sample means, right? What did we take? We took 30. Each of these data points here represents 30 pieces of data averaged. And what did we do? We did that 1,000 times, and then we plotted it. And then we did it more times and more times and more times and thousand times, plotted it. And if we were to do 10,000, generate 10,000 data plots, it would get even smoother. Okay. Okay, now it's telling me the standard error is 0.0385. So what would be 2 standard errors away from, this mean? Well, 2 standard errors away from that mean would be, let's see, let's plug that into a calculator. Okay, so I'm going to go 2.788 plus 788 plus 0.0385 times 2, and I get 2.865. Okay, so 2.865. I don't think I can write on this. Nope. Okay, I'm going to make a note of that real quick. Okay, so 2.865, that's my upper bound. Okay, what's my lower bound for 2 standard deviations? Okay, so I'm gonna enter the same thing and just subtract the numbers. I get 2 point.
Are you plugging in 0.0385 or 0.385?
Oh, shoot, you're right. I did it wrong. Thank you so much, Patricia. Okay, so 2.7. Yeah, I put the decimal point in the wrong spot. Sorry. Okay, so that's 3.558. There you go. Thank you. 3.558. Okay. Okay, and then 2.788. That's second entry minus. Okay, and that's 2.018. Okay, so we're getting a range of values there. Okay, this would be 95%. Okay, 95%. Okay. Okay, so let's build a confidence interval. Okay, the general form of a confidence interval is the statistic, okay, or what we call the point estimate. Okay, the critical value, okay, and the standard deviation of the statistic. And we usually call that the standard error. This guy is called the standard error. Okay. And this whole thing, the critical value times the standard error, this whole thing is called the margin of error. Okay, that's the whole thing is the margin of error. Right there. Okay, that's how much I'm going up and down. Okay, using X bar as our statistic for mu, we have X bar plus or minus Z star times, okay, the standard, this is the standard error. Standard error. Okay, Z star is how many standard deviations away from the mean do I want to be? Okay, like again, 95% confidence level is roughly 2 standard deviations away. Okay, or 2 standard errors. Okay, 95% confidence level is 2 standard deviations. Okay, so this 95% or okay, confidence level, that Z star for 2, okay, a Z star for 95%, I should say, is 2. Okay, it's really about 1.96, but 2 is fine. Okay, to start off thinking about this. Okay, so X bar is our statistic, okay, that we're using, and then we're going from X bar, we're going up and down a certain amount to find to locate what are the possible values for mu. Okay, now we can only use Z if sigma is known. We can only use Z if sigma is known. If sigma is not known, if we do not know the population standard deviation, okay, then we cannot use Z. We have a different parameter for that, and it's called T. Okay, and we'll get into what T is in a second. Okay, but we will have a different parameter T when we don't know the standard deviation. Okay, but if the standard deviation is given, then we use Z. Okay. Okay, finding critical z-scores from a confidence interval. Okay. Use the inverse normal calculation or StatCrunch to find your z-stars. Okay. So again, okay, let's say that we wanted to find out where is the cutoff. Okay, what are my z-scores for 95%, right? What are my z-scores for 95%?
Can I ask you a quick question?
Yeah, sure, absolutely.
Oh, thank you. So what if we don't know X bar either? Can we find that out?
Yes, you will always be able to find X bar.
Oh, okay, because there was like the last example on the homework that I wasn't able to figure it out.
Okay.
But okay, I guess
Yeah,
I can go back to that.
because generally, here's the thing. Here's my population, right? So that's what I'm using for my population. And if mu and sigma are given, then I can just use z. Okay, then I can just use z. But if only X bar and the standard error are given, which is my samples, right? Then I have to use t. Does that make sense?
Yeah, it kind of does.
And
I need to learn more.
Yeah, and if mu is given, then you know that X bar is given too, because that's a sample out of mu. Okay, it's easier to get a sample than it is to get the whole population. Let's take, for instance, a population of fish in a lake, right? Which is easier, to tag every single fish or to get a sample of fish?
A sample
A
of fish.
sample of fish, right? And the only way that I know the standard deviation for the population would be if I were to go out there and tag every single fish. Does that make sense?
Yeah, it makes more
Okay.
sense now.
Okay.
Thank you.
So sigma is generally not available in like real life scenarios. When you have data that makes up only like 100 pieces of data, say that you're running an experiment and you flip a coin or something like that, you have 100 pieces of data. Well, those are your 100 pieces of data. You know what sigma is because you only did 100 tries. But in the real world, sigma is extremely hard to get. And so our the next best thing is to just use our sample data. Okay, but X bar will always be given because you'll always have at least one sample to work with. Okay. Okay, so going back to where are my z-scores? Those are my z-stars. Okay, my z-scores. Where are my z-scores for my confidence interval? For a 95% confidence interval, what would be my limits here, right? Limits. So what I want really is I want to find for a normal curve, okay, remember this is z, right? Z is normal. I want to know what's the cutoff. What's the cutoff? Negative z and positive z. Okay, what's that cutoff for 95%? I want to know what's the cutoff for 95%. Well, let's use inverse norm to get that cutoff. Okay, so if the middle is 95%, then aren't the tails 5%? Aren't the tails? This is together, those tails make up 5%, right? So I have to take that 5% and I've got to do what? I've got to slice it in half. And so this is 2.5%. How do I make that a decimal? 2.5%. Well, that's 0.025. Okay, 0.025. And this is also 2.5%. Okay, or the upper part is 0.025. Okay, so what I can do is I can use the inverse function on either StatCrunch or the calculator, inverse norm, okay, to get me my z-score, right? We're going from probability, okay, can't write today. Can't write any day. Okay. Inverse norm. Okay, so let's see how this is going to work. Okay, so let's go to second. Let's turn it on first. Let's go to second vars. Okay, inverse norm. Okay, and what's the area? What's the area to the left that I want to look at? Well, I could either include the 95% or I could not include it. I could either get negative z or positive z. I'm just going to go with negative z. It's just easier. So the area to the left is 0.025. This is a z score. So I'm going to let mu be 0 and sigma be 1. And I'm going to click paste. And it tells me, look, your lower bound is negative 1.96. That's what that is. Okay, negative 1.96. Okay, which means your upper bound is going to be the same thing, but positive 1.96. This is called my Z star. This is my Z star for 95%. 95%. Okay, it's my Z star for 95%. So if we go down here to our confidence level is 95%. That means that 1 minus 95% is 5%, right? Which is alpha. If I take alpha divided by 2, I get 0.025. And if I plug 0.025 into the calculator, I get a critical value of 1.96. We usually take the positive number as our critical number. Okay, we don't usually take the negative. We take the positive because we want to keep things positive because we're positive people.
Can we go back to the calculator, what you typed in?
Yeah, sure. So all I did was go second vars and then inverse norm. Okay, and I just typed in 0.025, 0, 1, and on the newer versions, you may have to put left.
Okay, thank you.
Sure. Boom. Okay. So at 90% confidence level, the z-score is negative 1.645, or is positive 1.645. Alpha is 1 minus 0.9, which is 0.1. Okay, for 99%, if I want to be 99% confident, then my critical value is 2.575. Okay, alpha is 0.01. Okay, so find the critical value for some of these other ones. I don't know how important it is to get some of these other ones, but maybe we'll do maybe a couple of these. Okay, so if I wanted to get the critical value for a 98% confidence, I want to be 98% confident that I cover all of the data. Then how much is left over in this little piece down here? What percentage is left over there? Is it 1% or is it 2%? Yeah, it's 1% because it's half of the difference. It's half of the difference. So this is 1%. So this is going to be inverse norm of the decimal, which is 1% of 0.1. And if I were to do that in my calculator real quick, second entry. I'm just going to go 0.01 this time. Okay, and I get negative or negative 2.32, so I'm going to make that positive 2.32. Okay, so that is Z star for 98% confidence. Okay, Z star for 98% confidence. What about 80%? What would 80% look like? 80% confident. Okay, what would my Z score for 80% confident? Well, what's the lower percentage here? What's the lower percentage?
10%.
Thank you very much. It is 10%. And 10% as a decimal is 0.10, and a 0.1. Inverse norm that baby. Okay. And I'm going to go 1, 0 this time. And I get negative. Oops, not negative. I keep 1.28. I'm just going to leave it like that. It's positive 1.28. The z-score, these z-scores are always positive. Okay, always positive. Okay. I'm not going to do 99.5. We never really use that. 90%. Well, what's the critical value for 90%? Ho ho ho. It's already up here, right? It's 1.645. Okay. And on the exam, you'll have these notes for reference. So you won't have to derive a lot of these again. Okay. So these are my Z stars. Okay. They're the stars of the show. Okay. Okay, so let's use these stars of the show to get some confidence intervals. And then we got to interpret, well, what the heck is this thing, confidence interval? What does it tell me? Why are we even doing all this stuff? What is it good for, right? That's what math students always want to know. Like, what is this stuff good for? Okay. Example 2. Suppose we wish to estimate the average math SAT score for students at a local high school. Okay. We want to say, okay, what's the average math SAT score? Okay, it is a math class, so we're going to go with math, not English. Okay. We randomly sample 40 of 850 seniors who took the SAT at the high school. Okay. Okay. Personally, I wasn't real motivated to take the SAT because I was going to go to a community college anyway. You don't need SATs, at least when I was going, you didn't need SATs to get into community college. So, yeah. So, but all my friends who all went off to like UCSB and stuff, they were like killing themselves over trying to get a good SAT score. And then when I went to community college and I brought my math book home and I saw that they were actually learning out of the exact same math book, I'm like, oh, so all of that cramming and all of that money got you the exact same textbook that I am studying out of for 1/10 the price. Interesting. Anyway, I digress. Okay. I'm just a big proponent of community colleges. I guess I should be. Anyway, so suppose we wish to estimate the average math SAT score. Okay, at a local high school. We randomly sample 40 of the 850 seniors, right? So randomly sample 40 of the 850 seniors. So N is equal to 40, right? Does that make sense? My sample size is 40 here. Okay. Okay. Out of the 850 seniors, the 850 seniors, that's my entire population. See, here I know what the entire population is. Okay, the entire population, or big N, is 850 seniors. Okay, 40 seniors is my sample. This is my sample size. This is my population size. Okay, so 40 is the sample size and 850 is the population size. Okay. We find that the mean score of the sample is 438. Wow, that's really low. Is it? Is it really low? I don't know. It used to be a high score was like it used to be that you got 200 points for just breathing. They gave you 200 points for putting your name on the paper. Okay, and then like a perfect score was like 800. So I don't know, maybe things have changed. Okay, so we find the mean score of the sample of the sample, okay, to be 438. So of this one sample, that's our mean, 438. Suppose we also knew that the standard deviation of the population is 105. Build a 95% confidence interval to estimate the mean math SAT score for the entire senior class at this high school. Okay. Okay. So when I'm building my confidence interval, it's X bar plus or minus Z star times sigma over the square root of n. Now, why am I using Z? Because sigma is known. The standard deviation here is sigma, and that sigma is known. They gave us the standard deviation, therefore I can use Z. I can use a normal curve. Since I have sigma, I can use normal. If I didn't have sigma, I couldn't use normal. It wouldn't be normal. It'd be abnormal. Okay. Okay. So what is n on the bottom here, though? What is n? That's why I want to make reference to the difference between these two n's. What is n? Is n my sample size or my population size? Sample size or population size? Okay. We do have emotes, right? Like you could be like emotes. They should have like thumbs up and thumbs down somewhere, don't they? Right? They have like, here's a thumbs up and here's a thumbs down. And you, sir, are thumbs down. Okay, anyway. Okay, so I think that's a poll. Poll the audience or something. I don't know. I don't know how to do it. I'm in the wrong mode. Oh no, here, polls. Add a question. I don't want to add a question. There should just be emotes. Where are the emotes? I don't know. Who knows? Whatever. Okay, so this on the bottom here is sample size. Because we're making a prediction about the entire population, it's sample size. It is not population size. I do not want to use big N here. I do not want to use population size. Okay, so let's do the computation here. What was the X bar? What was the sample mean? This is sample mean. What was the sample mean? It was 438. Okay. Plus or minus, what's the Z star for 95%? I'll give you a hint. It's close to 2. It's close to 2. What's the Z star? What's the Z star? Yeah, it's 1.96. Okay, and just go back to the chart. Okay, see the chart right here, 95%, 1.96. There you go. Okay, 1.96. Okay, what was the standard deviation? It was 105 over the square root of 40. Okay. I'm like, oh, nice. Okay, So this is going to be 438 plus or minus 1.96 times 105. I'm just writing the exact same thing. It's kind of dumb. Okay, I'm going to plug this into a calculator. This again is called the margin of error. Okay, that whole thing is called the margin of error that we're adding and subtracting. So I want to add and subtract the margin of error, 1.96 times 105 divided by the square root of 40. Okay, that's going to be 438 plus or minus about 32.54. I'm just going to go out 2 decimal places, 54. So I want to add and subtract this, 438 plus 32.54. Okay. Okay, so let's do 438 minus, let's do the minus first, 32.54. That's 405.46. And let's add 32.54, 438, plus 32.54. That's 470.54. Okay. So what does this tell us? Okay, what does this tell us? What is our conclusion? From here on out, we have to have an interpretation. Okay? We must interpret our results. This is not my answer. Not my answer. Okay, now when you do your homework, it may want this as your answer. Okay, but on the exam, this is not your answer. On the next exam, you're going to have 5, is it 5? Yeah, it's 5 free response problems in which you're going to work out, okay, or type out, okay, various steps to finding confidence intervals and hypothesis tests. So this is only step 4 in the process. Step 5 is the conclusion. What's my conclusion? Well, my conclusion is that given that the means are approximately normal, okay, that the sample means are approximately normal, and this guy here is X bar, which is 438, then I am 95% confident, 95% confident that the true mean, mu, which I do not know the true mean, that the true mean is somewhere between these boundaries. It is somewhere between 405.46 and 470.54. It is a way to estimate the true population mean. It's an estimate. It's saying, look, do I want to look in the pool for my keys? No. How close do I need to be to look for that true mean? Where is that true mean? We are hunting for true means because that's really what I care about. In the very beginning, it says, estimate the mean. Sorry, in the problem, it says, estimate the mean for the entire senior class at the high school. Estimate the mean for the entire senior class. Well, I can be 95% certain that this senior class was between these two values. And I have to write this up in a sentence. And I say this, I say I am 95% confident. I am 95% confident that the true mean at the school is between 405.46. I'm going to run out of room, but whatever. I'll just round it. I'll round it to 405 and 471. Boom. It's good enough. Okay. It says, hey, this is am I going to look at 600s? Probably not. Probably 600. Probably this is probably not one of the top performing schools in America. Okay, when it comes to math SAT scores. I'm going to look here. Now, could the true mean be 600? Absolutely. The true mean could be 600. Hell, it could be 800 for all we know. But we'd only be 0.000001% sure that it would be 600. Does that make sense? This is a good place to look. Okay. Okay. We have a particular problem with using z-scores. Okay. And z-scores are only available if we have the population parameters. If we have the population standard deviation, which almost never happens. Okay, it says, how do we not know mu, the population mean, yet we magically know sigma, the population standard deviation? This almost never is going to happen. Okay, it's almost never going to happen. That's the case. If we don't know sigma, we can use S. What was S? S is the sample standard deviation. In our case, it's the sample error. Okay, it's the sample error, but it was all good. We can just call it sample standard deviation. Okay, I think on the exam they call it sample error. So just know the difference between margin of error and sample error. Okay, if it just says sample error, it's the standard deviation. Okay, and it's S. Okay, or on your calculator, it's S sub X, right? Remember that? Remember S sub X? Yeah, that's your sample standard deviation, right? Sample standard deviation. Okay, we rely on the fact that Z is equal to X bar minus mu over the sigma over the square root of n. Okay, has standard normal distribution, but this guy right here, if we just rely on the parameters, okay, we rely on the statistics, it is not normally distributed. But it does have something called a T distribution, or a student T. Okay, T, that's a T, lowercase t. Okay, let me rewrite my student here. That's a student T distribution. Okay, I think it's students. I don't know. I have to look it up. Okay. But anyway, it's the student's T distribution. Okay, it's a T distribution. So let's see, what's the difference between a Z distribution and a T distribution? Okay. This guy, X bar minus mu, where we do not have, where sigma is unknown, but S is known. This guy here follows something called a T distribution. T distribution. A T distribution, how does it compare to a Z? Well, what does a Z look like? A Z looks like this. No, it doesn't. Try that again. A Z looks like this. Okay, nice mean, nice tails. There's some, oh my gosh, I can't believe I just did that. Come back. Just trying to make it a little nicer. Okay, so here is Z, right? Z. Okay, there's your nice Z distribution. Okay, your normal distribution, right? This is your normal distribution. It says, hi, I'm normal. Okay, that's what this distribution is saying. Hi, I'm normal. Okay, just like SpongeBob. Okay, I'm normal today. It's good. Okay, and then what's the T distribution look like? Ooh, I'm glad you asked. Okay, here is what the T distribution looks like. Okay, it looks like this. Okay, what do you notice? The peak isn't as high, and the tails are much wider. They're much further from the ground, right? Okay, now the area under this is still 1. The areas are the same. Okay, they all add up to 1. But for the T, it's more spread out, and the tails are much bigger. Okay, much wider tails. I like wide tails and I cannot lie. Never mind. Okay. Okay. So wide tails here. They're very wide. Okay. So this guy says, hi, I'm normal. This guy says, hi, I'm not normal. Time for tea. Okay. It's tea time. Okay, I'm not normal. Maybe he's not normal because he's British. He's like, well, it's tea time. I'm British. I'm not normal. So this guy over here, maybe he's American. He's like, oh, I'm normal. So that seems like a very self-centered, egocentric, like Americans always think they're normal, right? They go over to another country and they're like, what's your accent? What country? And they're like, well, what's your accent? And Americans are like, I don't have an accent. I'm like, yeah, you do. You have an American accent. What is wrong with you? So anyway, I digress. Okay, so get it? Z and T, different distributions. T, I apologize for that. Okay, T is not just one curve. Here's the idea. T, depending on the sample size, T depends on sample size. Okay, T depends on sample size. The shape of the curve depends on the sample size. Okay, and so it depends on something called degrees of freedom, which we really don't have to go into a whole lot in this class. Just know that the calculator and StatCrunch, they will compensate for degrees of freedom. It's not anything that we have to really worry about. But know that there is a difference between degrees of freedom and sample size. Okay, they're off by 1. Degrees of freedom is n minus 1. And sample size is n. Okay, so when it asks for degrees of freedom, that's n minus 1. When it asks for sample size, that's just n. So degrees of freedom, take 1 away from the sample size. Okay. Okay. So if the the distribution of x bar when sampling 30 values would be t sub 29. Why would it be c sub 29? Because it's 29 degrees of freedom. It's t of 29. Okay, we reference t based on its shape, and it's the 29th shape in the series. Okay, it's a family of curves, what we call it. We call it a family of curves. Okay, again, it's not that important that you know that. Just know how to work with it. That there is something called degrees of freedom, and it is n minus 1. Okay. Okay, so to build a one sample t interval, okay, very similar to what we did before. But instead of this time, we have a t star and we have an s. Whereas before we had z star and we had sigma. So, okay, if sigma is known, then we have z star and sigma. If it's unknown, if I should say only s is known, only s is known, then we use t star and s. Okay, if only s is known, then t star and s. Sorry, that t looks bad. Okay. Okay, let me skip that for right now. Okay, let's find the critical value needed to build the t interval. Okay, we want to find an 80% confidence interval. Okay, remember only s is given. Okay, right? S is only given. There's no sigma given. Okay, for any of these. Maybe I'll put that over here. Okay, build a t interval, right? So only s is given. Okay, we want a t confidence interval this time. Okay, so t star of 29. So that's going to give me some sort of curve. Okay, family of curves. Okay, and I want 80% in the middle, right? 80% in the middle. Okay, so how could I find the t star value, t star of 29, using the calculator? Well, it's the same process, but instead of inverse norm, it's inverse t. Look at that. And it should be the one directly below inverse norm. The one directly below inverse norm should be inverse t. Okay. Okay, so let's pull that up on the calculator. See what happens here. Okay, so we have, okay, inverse, I'm going to go second vars and then inverse t this time. And it says, what do you want the area to be? Okay, so what do we want the lower area to be? Well, we want the lower area to be 10%. The lower area will be 10%, which is 0.10. And then it asked me for the df. Like, what's the df? What do you think the df is? Yeah, you're right. That's degrees of freedom, right? So the degrees of freedom in this case is 29. That means that there were 30 samples, right? The sample size is 30.
But don't we subtract a 1?
No,
Not,
when it's the subscript for t. It's already been subtracted.
oh, okay.
Okay. So the degrees of freedom here is 29 because it's already been taken into account. And then I hit paste. Okay, so 29 is the degrees of freedom, n would be 30. Okay, so again, we go back here and it says what? It says t sub n minus 1, right? T sub n minus 1. So if it's t sub 29, then n would have been 30. Okay, so what is the inverse t here? It is negative 1.31. I'm going to use the positive to keep things positive until I get 1.31. Okay. Okay, what's the t star for a 95% confidence interval? 95% confidence interval, so 95% in the middle means that it's 2.5% on the edges, right? And it says n is equal to 12. So what are my degrees of freedom if n is equal to 12? Yep, it's 12 minus 1, which is 11. Okay, 12 minus 1, which is 11. Okay, so let's plug this in, okay, to the calculator again. Okay, so second bars, inverse t, okay, oops. Clear that out. Second bars, inverse t. Okay, what's the area? The area needs to be put in a decimal, 0.025. What's the degrees of freedom? The degrees of freedom is 11. Okay, let's paste that. And it comes out to negative 2.2, basically. So this is 2.2. Okay. Okay.
Can you show us on StatCrunch as well?
Yeah, let me see.
Because I can't figure out on my calculator, where do you put paste? I found the T distribution, but I have the IT83 Plus, the older version.
Okay. Oh, okay. So if you have the older version, you have to plug it in a list. Okay, so you have to do this. Let me show you.
Okay.
real quick. You have to do. I'm gonna grab this up here, right?
Mm-hmm.
And it'll do inverse t, delete, 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 delete. So it'll come up like this for you, right?
Mm-hmm.
And then what you do is you plug it in as a list. So 0.025,
Right.
comma, 11, and then close the parentheses and hit enter.
Okay.
Okay.
Oh,
Okay, let's see what StatCrunch does. I don't know if it will calculate a t-score or not.
it will. I actually know how to do it. Don't worry about it.
Oh, okay, okay, okay.
Yeah.
So
It's on there.
okay, perfect. Okay. Okay. Okay, so we want to construct a confidence interval. This is our 5-step process. Okay, define the parameter, choose the statistical method, check the requirements. Okay, independent random large. Construct the interval, the calculations, and then interpret the conclusion. Okay, 5 steps. Okay, the requirements. Is it independent? Are all of these sampled independently? Is there a large, is the sample small enough in proportion to the population size? Okay, so is it sampled independently? Sure, we can almost always assume that it's sampled independently. We can almost always assume that it's randomly sampled. Otherwise, we wouldn't have a problem. We couldn't do anything. Okay, we would be able to do no math. If these two weren't satisfied, we would not be able to do any math. So in all the problems that you're going to be given, these are basically satisfied. Okay, is the sample large enough? Okay, is n greater than or equal to 30? That's good. Okay, is n less than or equal to 30? That's not as good. Okay, it's okay as long as a couple things. We can use a sample less than 30 if we know that the parent was normal. Okay, if the population that this thing came from was normal, then we can use less than 30. Or if we know that it's symmetric. Or if symmetric. We can't use skewed distributions that are less than 30 data points. It's just not going to happen. Okay, but again, I'm really not going to give you a problem where you stop here, because no math would be done. Okay, step 4 would be to do the calculations. Step 5 would be to do the conclusion. Well, what are the conclusions here? The conclusions would be, we are blank % confident, this should say confident. We are, say, 95% confident that the interval from, say, A to B actually contains the true mean, okay, or true proportion, or true standard deviation, or true whatever we're looking for, whatever parameter we're looking for. Okay. Okay, to estimate a mean mu, it's t statistics. We're always going to use t, okay, unless okay, sigma is known, which is almost never happens. Okay, then use z, unless sigma is known. Okay, to estimate a proportion, we're going to do a proportion statistics, and we're not going to get into this until Thursday. This will be Thursday. Okay. Okay, example 4. Okay. Example 4 says, the listed below are the speeds, miles per hour of cars measured, okay, from the 5 freeway near Santa Ana, California. This simple random sample was obtained at 3:30 p.m. on a weekday. The speed limit for this road is 65 miles per hour, okay? So how much data do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's n, right? N equals 12, okay? Do I know the population standard deviation? Do I know the population standard deviation? Do I know, is sigma known? Sigma known? No. Sigma is not known. Only the sample, okay, is known. I could calculate it by hand if I really wanted to, okay, for the population. But this is just the sample, not the population. This isn't the whole population of cars that are on the freeway at 3:30 p.m., right? That would be thousands of cars. Does that make sense? Your population is huge here, okay? Right? Especially at 3:30 p.m. going north. Okay? I mean, that's a parking lot, right? Everybody agree with me? No? Sounds good. Okay. Oh, thank you, Jared, for that. Onlinestatbook.com. Okay, perfect. Okay, so it's not known. This is not known. So we're going to use Z or T here. Are we going to use Z or T? We're going to use T. Okay, T. Okay, T for the win. FTW. Does anybody say that anymore? I don't think so. That's so like 2012 or something, you know, whatever. Few people ever did. Oh, okay, that's great. Thank you for that. I'm one of those few people, I guess. Okay, the same few people that say awesome sauce. Okay, also the same few people that say bitchin', right? Or totally tubular. That was a thing. Yeah, exactly. Okay. Is that Kaiser or Pumpernickel? No, I was kidding. Okay. Use the data to construct. There you go. Okay. Yeah, let's just get back to the math, okay? Because I don't want to not be stoked. Okay, like for sure. Okay, use the data to construct a 95% confidence interval for the mean C. We're going to use a t distribution here. Okay, and how many degrees of freedom do I have? How many degrees of freedom do I have? Well, n is equal to 12. So what are my degrees of freedom? My degrees of freedom, okay, my degrees of freedom are 11, right? My degrees of freedom are 11. Okay, very important. T distribution. Why t distribution? Because we have no sigma. I know I keep saying the same thing over and over again, but I will bet you $1,000 that there will be at least one person on the exam that will mix that up. It always happens every single time. So there you go. Why 11? Because the degrees of freedom is n minus 1. It's the sample size minus 1. There's 12 pieces of data, and the degrees of freedom is n minus 1. Okay, t distribution for no sigma here. Okay, if you have sigma, you use z. If you don't have sigma, you use t. It is tea time. Questions? Oh, okay, sounds good. Okay. Okay, so we're going to have x bar plus or minus t star. Okay, t star. Okay, x bar plus or minus t star. Okay, times s over, that's the sample standard deviation, s over the square root of n, right? Square root of n. That was that's our formula. Comes to us from up here. Okay, right here. This is our formula for building an interval. Okay, so we just got to kind of plug in what we know and what we don't know. This is a 95% confidence interval. Okay, so we have to find out what t star is. T star for 95%. Did we do that already? Did we find some t stars? No, we did. Oh yeah, we did. We did it for 95 at 11. Look at that. That's great. That's called forward thinking in your notes. You're like, we already did that. For 12 items, we did a 95% confidence interval. Boom. So what's t star? T star is 2.2. That's beautiful. Okay, t star is equal to 2.2. C above, like way above. C way above. Okay, t star is this. Okay, so what's x bar in this case? X bar is 60.67 plus or minus, okay, 2.2 times s, which is 4.08, over n, the square root of n. What's the square root of it? What's n here? N is 12, not 11. The degrees of freedom are 11, n is 12. So I'm going to find my margin of error here. Okay, plug that into a calculator. Okay, so 2.2 times 4.08 divided by the square root of 12. Okay, this is what I'm going to add and subtract. So I'm going to add and subtract about 2.59. There. About 2.59 from 60.64. Or 67, sorry. So the lower one is the subtraction. So 60.67 minus 2.59 is about 58.08. Okay, give or take. Okay. And then what about this guy here? 60.67 plus 2.59. 60.67 plus 2.59 is about 63.26. Okay, 63.26. Okay, again, I'm not done. I have to write a conclusion. What's my conclusion? We are 95% confident that the true mean or the true average, I got two of those, true average speed at 3:30 p.m. is between 58 and 63 miles per hour. Okay, which there's no way in hell that that is. Well, maybe there is. Maybe there is. Okay. It depends on which direction you're going. So, okay. Okay.
Can you show where you got the 2.2 for the T star?
Yeah, it's right up here in example 3. See example 3. Yeah, good question. See example 3. See way above. See example 3. Okay.
Professor?
Yeah.
So just to clarify, whenever we use the inverse T on the calculator, that's just to find the T star?
Yes.
Okay, thank you.
Okay, now let's go to the next one here. Okay. Example 5, we're going to cheat. We're going to cheat because the calculator will actually give you the interval if you just plug in the parameters. Okay, so let's look at this one. A machine at a soft drink bottling company is calibrated to dispense 12 ounces of cola into cans. A simple random sample of 35 cans is pulled from a line after being filled and its contents are measured. The mean content of the 35 cans is 11.95. So what is that? What is the mean? 11.92. How would I represent that? 11.92 is represented by what variable? Is it mu or is it x bar? Okay, it's x bar. So x bar is equal to 11.92, right? Okay, what's the sample size? N. What's the sample size N here? The sample size is 35, right? Sample size is 35. Okay,
Professor-
yes.
Sorry, how did you know that it was X bar and not mu?
Because it said the mean content of the 35 cans, and the 35 cans is my sample, right?
Mm-hmm.
So you remember that we have parameter is mu and sigma. Sample is x bar and s.
Okay, thank you.
Right? And the x bar comes from our sample.
Okay, thank you.
Sure. Okay, so we have 11.92. Okay, n is equal to 35. Okay, and so I also have a sample standard deviation. Sample standard deviation. This is not the population standard deviation. It says standard deviation, right? It says standard deviation. So you're thinking, oh, that must be sigma. Sigma equals 0.085. No, wrong. It is not. That is S. Okay, that is not sigma, that is S. Why? Because all we have is a sample of 35 cans. I didn't pull off, you know, every single can in the factory. Okay, that's a lot of cans. I'd be there the rest of my life. Okay, trying to average those things. Okay, I pulled off only 35 cans, so this is the sample standard deviation. If I'm only given the sample standard deviation, then this is a T interval. This is a T interval. Okay, T interval. And what I can do is I can use the information on the calculator to calculate my confidence interval. Okay, we don't have to do it by hand. We can just use the calculator. So here's how we do this. We hit stat. I really need to find a way to not let that go away. Okay. Stat. Oh, you know what? Let me just be smarter than the average bear here. I'm so used to being on one side of the screen. There. Yay. Okay. I hated the fact that that thing disappeared all the time. Okay, stat, right? We're going to go to stat, and then we're going to go to test. Test is. We're going to go to tests, and we're going to go to something called T interval. T interval. Okay, stat, test, T interval. And that is number 8. They are all the way down to 8. I get T interval, which is 8. Okay. Okay, I don't have any data to plug in. I only have statistics. Data would be the raw data. I don't have raw data. So I'm going to use stats, and I'm going to hit enter for stats. Okay, and it asks me what? It asks me 4 things actually. Okay, it asks me what's my sample mean? Well, my sample mean in this case is 11.92. Okay, cool. Okay, what's my sample standard deviation? 0.085. What's my sample size? It's 35. The calculator will calculate the degrees of freedom for you. Okay, don't worry about that. It's smart enough to subtract 1. Trust me. Okay, and the confidence level. Now, the confidence level can't go in as a percentage. It has to go in as a decimal. So what is the confidence level? Is it 95%? No, it's 99%, right? It's 99%. So I'm going to go 0.99, and then I'm going to hit calculate. Okay, and it tells me, oh, we are 99% certain that between 11.881 and 11.959 is the average ounces in the cola, right? The average ounces in the cola. Okay, we're 99% certain that what? That we're getting ripped off. Right? Because again, we have to put this in context of the problem. Raw numbers mean absolutely nothing without the context of the problem.
I have a
So,
question.
yeah, go ahead.
The sea level, why is it 0.99?
Yeah, because it says right here, 99% confidence.
Oh, sorry. I didn't see that. Thank you.
Yeah. Okay, and so we say our conclusion, you must have a conclusion, and the conclusion must be dependent upon the scenario. You can't just say, we're 99% confident that it's between these. No, we're 99% confident. We are 99% confident that the true amount of soda in the cans is between 11.881 ounces and 11.959 ounces. Okay, which means we're getting ripped off. Okay, if they claim that it's a 12-ounce can, I want a 12-ounce can. I don't want no 11.88-ounce cans. Okay. Okay. Okay, let's wrap this up with margin of error. Okay, what's the margin of error gonna be? Okay, remember the margin of error.
Excuse me, on the last one we just did, is there any way to do it on StatCrunch, or do you know?
Yeah, we can do it on StatCrunch. Absolutely.
Okay.
Yeah, let's do that on StatCrunch. Absolutely, this is easy on StatCrunch. Super easy. Easy peasy. Okay, so we're gonna go to calculators, right? Or t-stats, is t-stats? No, that's hypothesis test. Calculators, and we're gonna go down here to T. Okay, T, for a T distribution, okay? Now, we wanna be, what do we want? No, we don't want T distribution. What do we want? We want a confidence interval. Where is that one? I don't want just T. Nope, 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 nope. Where's confidence intervals? Data. No, I don't want data. Where's edit? Sample, varied regression. Should be calculators. Okay. Okay, let's see what we got here. Okay, so they give you the degrees of freedom. Okay, we want between. And we want to know, yes, here we go. Okay, so gosh, I thought that they would be able to. We want 99%, right? 99%. What's 99%? 0.99. Okay, so 0.99, and the degrees of freedom was 11. Okay, so yeah. So unfortunately, you do have to do a little bit more computation. Because this is just going to give you a z-score or a t-score basically. And you're going to need to convert that t-score back into, because it doesn't, it won't. Yeah. Because what you're going to have to do, yeah, you'd have to multiply by your sample standard. Yeah, you'd have to multiply by your standard error, and you'd have to, and then you'd have to add. So you would have to actually do a lot of work backwards on this one. Yeah, I don't know why they don't have it. They should. Let me Google it real quick. I could have sworn they had a confidence interval. Which one is this? Click stat t-stats. One sample. Oh, that's how we do it. One sample. Okay. Okay. Stat t-stats one sample. Okay. Let's try that one. T-stats one sample. Okay. With summary. There we go. That's what we want. It's one sample t-stats with summary. Okay. Now we're good. And we don't want a hypothesis. I thought this was just for hypothesis test, but it'll give me a confidence interval. There we go. That's what I want. So let me go back. Okay. So it was t-stats one sample. Okay, and with summary, because we don't want data. We want summary data. Okay, and it'll say, okay, what's your sample mean? Your sample mean.
Can you go back real quick so I can take a picture of that?
Sure. So t-stats one sample with summary.
Thank you.
Okay. So you go sample mean. What was your sample mean? It was 11.92. Okay, oops, sorry. What was your What was your sample standard deviation? It was 0.085. What's your sample size? Your sample size is 35. Okay, I believe. And what's the confidence level? The confidence level I want is 99%. Okay, and so I just click, oh, this is 11.992. 0.92, and then I just click compute. Okay, and it tells me that my lower limit is 11.88 and my upper limit is 11.96. Okay, so it was 11.881 and 11.959. So there you go. Yes, I knew there was an easy way to do this. Okay, just forgot temporarily where it was located. Okay. Okay, let's move on to the last page here. Okay. Here we want to find out, well, what's our margin of error? Okay. What's our margin of error and how big of a sample do we need for a certain margin of error? Okay. The larger the sample, the smaller the margin of error. The larger the sample size, the smaller, okay, the smaller the error becomes. Okay, a lot more samples, a lot closer to the true mean. And that's what we saw. We saw in our, when we ran that, let me go to my history here. Where's the other one? I don't think we kept it. Oh, well, whatever. Okay, when we went and did our little simulation, right? The larger the sample, the better approximation we got. Right? That means that the error on the distribution is going to be a lot less the higher the sample size. So we want to know, okay, how to find the sample size for a given error. Okay, for a given error. So let's look at the formulas for sample size. Okay, we're just taking this formula for the error. Remember, this error is really just X bar plus or minus T star, right, times S over the square root of N. That is E. They're calling this E for error. Okay, it's really margin of error, but they're calling it E for error. Okay, that's how much error we're off, plus or minus. Okay. When you hear on the news, it's like, you know, we're 98% confident that, you know, all politicians are liars. Then, you know, within plus or minus 5%, right? When you hear that plus or minus, that's what they're talking about here. They're talking about an error, right? So right, it's that plus or minus 5% or plus or minus 2% or, you know, plus or minus 5, you know, like the average is 35 plus or minus 5. What does that mean? It means 5 above or 5 below. It's within a range of 10. Does that make sense? That's the error. That's the error of my guess. That's how confident I am in my guess. If I have a huge range, then I'm going to capture a lot of values, but, you know, not real confident. Okay, smaller range, more confident in my guess, in my estimate. Okay, okay. So X plus or minus T squared or T star. Sorry, that's a star. T star S. So we want the error. So we don't know how to minimize this error. We want the error within a certain boundary. So here's what we do. We say E is equal to T star times S over the square root of N. Okay, and with a little bit of algebra, we want to solve for N. Okay, so don't get all freaked out on me when I start doing the algebra. Okay, so we get the square root of N times E is equal to, we'll call this T star S. Okay, divide by T, or sorry, divide by E, that's the error, E, not T. And E's and T's are looking like the same. Divide by E. So I get the square root of N is equal to T star S over E. So N is equal to T star S over E squared, okay? And we always want to estimate up and not down. We want to estimate up, so I'm going to put a greater than or equal to sign here. Okay, we always want to round up to the nearest whole number. Round up to the nearest whole number. Okay, and this is a T. I don't know what my T's and E's look like each other, but that's my T star. Okay, round up to the nearest whole number. Okay, so this was division by E. Okay, cancel you out. Square both sides, get rid of the square root. Okay, so I'm going to use this formula. Okay. Okay, now, what if sigma is, this is if sigma is not known. Sigma is unknown. Then what if sigma is known? If sigma is known, then N is greater than or equal to Z star sigma over E squared. I just changed the S to the sigma and the Z star to the and the T star to the Z star. Okay, and I do apologize for my sloppy handwriting. I'm trying to do the best I can with this pen. When you spend 30 years on a chalkboard, or a whiteboard, moving modalities becomes more difficult than if you're like younger. I've noticed that. So I guess I'm just getting old. Whatever. Okay. An IQ test is designed so that the mean is 100. Okay, so the mean is 100. And the standard deviation is 16. So they give me the standard deviation of the IQ test is 16 for the population of normal adults. So the mean for a population of normal adults, right? So are we talking about a sample or are we talking about the population? We're talking about the population for normal adults. So what is 100 going to be? It's going to be mu, right? Mu is 100. Okay. What is the standard deviation? Sigma here is 16. Okay, find the sample size necessary to estimate the mean IQ score of statistics students such that it can be said with 99% confidence that the sample mean, X bar, is between or within plus or minus 4 IQ points, right? So X bar is plus or minus 4. Okay, assume that sigma is equal to 16. Okay, so I want to get N. I want to get the sample size. Okay, it says find the sample size N. So N, I'm going to use this bottom formula here. Okay, n is greater than or equal to z star. Okay, z star. So z star times sigma, what was sigma? It was 16. Over the error, what was the error? What was the error? The error was 4, right? This is the error. This is E. That's the error that I'm looking for. That's 4. Okay, and then I'm going to square this. Okay, so this is z star for a 99% confidence interval. I want to be 99% confident that this is my margin of error. So how many people do I need to interview, or how many people do I need to test, okay, so that I'm within 4 points, okay, plus or minus 4. So this is 16 divided by 4, right? So this is going to be n is greater than or equal to 4z star squared. Okay, so now I need to know, well, what's z star? Well, what's z star for 99%? What was z star for 99%? Well, if you don't remember it, that's fine. I think it's 2.56, but we can easily go back in and figure it out using inverse norm. Okay, so go to inverse norm. Again, what's the area? It's 1%, so I have to cut it in half. That's 0.005. Okay, what's this? This is just the same, 0, 1. Okay, and it's 2.58. 2.58. So I was close. I think I said 2.56. Okay, 2.58. So this is 4 times 2.58 squared. Okay, and then I want to round up to the nearest whole number. Okay, so that's 4 times. That's a time symbol, not decimal. Okay, so what's 4 times 2.58? Let's multiply this guy by 4. Okay, and now let's square him. Let's just hit the squared key, and I get about 106.1. I want to round up, not down. I want to round up, not down. Okay, so round up. Okay, round up. So we're going to say that it's 107 people. So this is greater than or equal to 106.15. Why do I round up to 107? Because I can't have 0.15 of a person, right? I either made it to 106 or I didn't. Does that make sense? And so if I make it past 106, I'm at 107 because people come in whole persons. Okay? Makes sense. And that's it. That's it for me. If you have any questions, please let me know. I'll stick around for a few more minutes, 15 minutes or so, to answer any other questions that you may have, but that's about it. Okay. Okay, homework is online through Canvas. And if you don't have any questions, you're free to go, and I will see you on Thursday. We'll finish up 8.3. Okay, which really isn't that long. Okay, we may get out early on Thursday. You're welcome. Thank you. I'm going to set up a breakout room. Okay, for me and Gabriella. Okay, so Gabriella, I'm going to make you co-host. Okay. Oh, you're welcome. Haha. Okay, so let's do a breakout room. I'm going to add a room and then rename this. This is going to be Gabriella's room.
Are we in a separate room already, or?
No, just
Okay.
let me know if you need help. Do you?
Oh, I
Well,
thought you were going to break us in different rooms.
I am. Just let me know. Is that why you're staying?
Yes.
Yeah.
Sorry about that. Okay, so I'm going to give you the ability. Should I just break you in half, or you can go into, Gabriella's room or my room? I'm going to open the rooms right now for that. Okay. So, okay, sorry. Who wants to be with Gabriella? Okay, anybody?
I'm okay with Gabriela. I'm okay.
Like picking teams.
With
Is it-
Gabriela is fine.
Okay. So, and then, yeah. So, or maybe I'll just randomly. Can I randomly like move participants automatically? There we go.
That's fine.
So, does that work? There we go. Okay. Okay. Where am I? I'm not in the room yet. What room am I am? Rosa, you are with Gabriella. Sorry.
How do I go there?
Gabriella. No, is that Rosa? Oh, how do you go there? Okay. I opened the rooms. Did they not get assigned? Let's see. One second.
Mhm.
Oh, here we go. Now you can go there. My bad. whoops, that didn't work. Okay. Okay, I'm gonna go to my room at this point. If I can figure out how to do that. I don't know why you can't go to a breakout room when you're sharing your screen, but whatever.